Okay, yeah, I'm Praneeth. I'm a faculty at MBZI along with Sam in here, and we're part of the Department of Machine Learning. I hold a visiting appointment at MIT, but I am more and more getting involved with MBZ as the day goes by. And I'm also involved with the ADIA lab for about close to a year, okay? All right, so the first two slides are a bit philosophical about the world that we're heading towards, or the kind of world we'd like to see. And then we'll get to some of the technicalities and present-day context of LLMs and so forth, all right? If you think about the current world we live in, I'm talking about the social world, right? Forget about computing and things like that. It's kind of a mix of silos. You have a bunch of silos that you operate with, and your whole life is always centered around these silos that are holding some data. These silos could be banks, they could be large companies, it could be a large data center, it could be some large company, and your whole life is revolved around however you're supposed to be interacting with them according to those silos. Okay, the world we'd like to move towards is a world of this kind, right? So if you want to talk to somebody, what would you do in the real world? You'll try to find someone that's relevant to you, you talk to them. If you're, say, walking on the street, if you're not digital yet. But if you're in a digital world, how do you enable these kind of seamless interactions? Like how can this happen seamlessly? What do I mean by seamlessly? I'm kind of emphasizing on this. So this is my second slide on being a little philosophical about this. So we live in so think about, does anyone know what that picture is representing, the one in black and white? It's not from many decades ago, it's a few decades back. Nope. Oh, well, that would have been a good guess. Well, the computers were huge too. That's a telephone exchange. So if you were to call someone, your family or your dear friend, or make an office call, you call the telephone exchange, you book a slot with them, and they're going to change wires around, and they give you a slot, and that's costly, not as cheap as today. And then you get a limited amount of time, and that's how they connect. They change wires, and that's how they put you in line with someone that you want to talk to. So you reserve your phone call a few hours, sometimes a few days ahead. That's how things were a few decades back. And then we are living in a world where we don't think about this, right? I mean, this sounds silly to us of what was happening, but that was the real world. Right now, everything happens seamlessly. Communication is taken for granted. Like, I call anyone who I want, okay? Where are we heading towards? Now, this is, again, the current world. This is now, right? We are living in a world with a lot of digital data being collected that's really siloed away across organizations, right? So this is kind of analogous to this kind of the communication era, right? This is like the beginning of data silos and the problems that is causing this. Where would we like to go? We'd like to have seamless collaboration. That's my emphasis on seamless. Like, you don't think about communication and how things work when you call someone. You shouldn't be thinking too much about collaboration in a digital world or privacy. Things should happen seamlessly, right? We're not there yet. We don't know if it's going to take another 5 decades or maybe like a few years down the lane. All right. So what enables us to get there? Okay. So let's get to some of the contextual problems of today, all right? So there's the large language models, which we all are been hearing about, the chat GPTs and so on and so forth. You've heard a bit about federated learning from the nice talk by Peter as an introduction. You'll hear more from Sam as well. So one of the important problems that comes up in the context of the previous slide is as follows. The current day large data and large training, what I refer to by pre-training here, is being done by really large, massive organizations that are very well equipped. Okay, it's not very democratized, or like it's not very participatory as to how these your engagement with the large language models is. What makes it more participatory is the current day process of fine-tuning, which is what you saw a little bit in Peter's slide. You download these large models, and then you fine-tune them to your personalized context, to your own local data. All right, but then there's a bunch of clients that could do that. How could a bunch of clients work in a participatory fashion in order to fine-tune and use these models? Okay, so maybe in one slide, think about you choose some large language model of your choice. For example, in the slide, we're showing Llama 3.2. You download Llama. That's the Llama is being trained by a very large party. You download Llama, and you can fine-tune it on some specific example. Maybe you want to fine-tune it on a public database of medical Q&A, like health-related Q&A, so that you have a Llama model that performs well for your context that you care about. Now, there's a bunch of clients that could do that. That's the participatory part of things. But how do you aggregate the knowledge of fine-tuning done by multiple models or multiple clients? right? So once you do that, then of course you can think about services that you could deploy. You could think about startups you could launch and products and so on and so forth, where you can, for example, have some sort of a chat bot that's the user interface that will let you ask all kinds of medical questions. And since your llama has been fine-tuned to these kind of medical questions, you get somewhat relatively better service. Right? So how do we do this in a participatory fashion? So that brings up the world of LoRa. Okay? So one predominant chunk of techniques that is very popular for fine-tuning is called low-rank adaptation. This is a picture taken from one of Sebastian Raschke's online books or reading material. What LoRa is in a slide, it's a reasonably simple idea, but it gives you a whole lot of efficiency in federated fine-tuning. When I talk about efficiency, I mean resource efficiency of the different clients, because these are large models. And these clients are less equipped with powerful resources, so how do they fine-tune in an efficient manner? The original regular fine-tuning, which is not resource efficient, is as follows. You download the model, so that's your llama. The pre-trained weights is basically your llama weights. You need to fine-tune, so you need to learn some sort of an update or a weight update, some sort of a modification to these pre-trained weights so that it performs well on your local data, which is like your medical Q&A, for example. But now, this is not efficient because this weight update is very large. It's equivalent to learning a weight update on a very, very large model. So what LoRa does is kind of very simple and elegant. I mean, this kind of ideas have existed for a few decades, but this is within the context of fine-tuning LLMs, which is you factorize your weight matrix as a product of smaller matrices. So if this was like m by n, you have a product of m by k times k by n, where k is chosen to be a reasonably small number, so that as long as you hold good utility in your fine-tuning. And so the amount of things that you need to learn is much smaller, which leads to efficiency. So that's fine-tuning. But this is not federated yet, because this is just one client. This is your device, or you in the classroom, or you in your startup, or you in your office. That's just one client. So how do you do this in the federated setting? That's where the whole idea of federated learning in general comes up. So this is just one slider. You've seen a lot about what federated learning is in the previous talk, which is you have a bunch of models being trained separately across different clients. There is some aggregation process that happens in the server, and then you have an aggregated model, right? So now you're going from one client to multiple models. But now let's overlap this with the LoRa, right? Because LoRa we saw in the previous slide was on one client. So fine-tuning with one client. But if you had fine-tuning being done by multiple clients on different kinds of Q&A data sets, how do you put this aggregate knowledge together so that you have a better fine-tuned model? So that's the question of federated LoRa. There's been some work in this area, and this is some late-breaking recent work from my lab. The reason I'm putting this particular work in this context is because this paper would be part of the poster session, and the students would be around whenever the session is, I guess, tomorrow. Okay, so one of the important problems that shows up here is as follows. The current status quo of what is happening, right, prior to the new update that I'll share you is as follows. The federation is being done in this sense. It's a weighted average of the client of the adapters learned by each client. So A and B are the smaller fine-tuned versions that are being produced by each client. Those are sent to the server, and in order to aggregate those adapters, you do a weighted average. Now you have a updated fine-tuned model that is federated. That's great. But if you think about it, there's something missing in here in the way the averaging is being done. Okay, so that's the elephant in the room. These are the young new students you'll be seeing at the poster tomorrow. So this is what is being done currently, the status quo. But what you really need is an average of the weights, not the average of the individual adapters that is going into your aggregation process. Federated learning, at least in the traditional or the classical sense, is about averaging the models, the final model weights, as opposed to averaging factors of your weights, right? So averaging a bunch of numbers is different than writing them down as factors and averaging out those factors separately. Okay, so these are not same. So this is something that was missed and not looked at by the community. So we identified this and we came up with an updated LoRa, which is called the Federated Exact LoRa, which enables the same kind of averaging, but with some modification in the process. This comes with the cost of additional communication, so an additional communication. So this is the scheme, okay? So the clients break down your model into two factors, right, into A and B. The A and B are sent from the clients to the server. The server aggregates them. Those are the averages of the A and B adapters. But now the server computes something in addition. So that is the W residual, which is the residual of what kind of average you wanted versus the kind of average that is currently being done. And you pay an additional cost in communication. You send that residual back to the clients, and the client needs to do some correction or some more update to their current process so that it results in a proper averaging, like an exact LoRa towards the end, right? You want a proper average in the end, right? That will fix a lot of LoRa variants that exist in the world where the averaging is a little off in the federated version of it. So you can fix those with this kind of a update, okay? So that's what you should be checking in the poster as to what that update would be on the client and why that would result in an exact averaging overall. Okay, so there's a quick picture or two that this is showing the discrepancy between the true average and the current averaging that is being done when the federated the LoRa models are aggregated in the federated sense. And you see the discrepancy is improved when you use FedEx LoRa. And that also shows up on results that kind of flows into the experiments that we've done with a bunch of large language models on different data sets, and these are ablation studies. You'll see more about this in the poster tomorrow. Okay, so now, as Peter pointed to, we're going to be talking about some variants of federated learning that kind of find a good positioning in today's state, a world where the models are getting larger and larger, right? The large language model world in the post-LLM era. What can be done in order to democratize or increase participatory nature of dealing with LLMs or engaging with LLMs during the learning process or the fine-tuning process and so forth? Okay, so we've done a lot of work on split learning along those lines. During my early PhD, I had some good payback kind of results from this kind of work. I was just thinking about what it means to apply split learning in the sense of LoRa, for the LoRa problem, for the fine-tuning problem, right? To increase efficiency further. So this brings up this kind of a systems diagram, which is as follows. So you train, so you have like a multi-server setting where you split your model between the clients that are doing the LoRa fine-tuning. So these are the clients that are doing the LoRa fine-tuning. And if fine-tuning itself was costly, say the model was so large that the client is having a hard time just doing fine-tuning, whether they use LoRa or not, that workload could further be split between another server and the clients themselves. But at the same time, the server would have a larger chunk of the model. More layers would be left with the server, while some layers would be with the client, and they're kind of organizing and kind of working in tandem. So what happens here is as follows. The clients perform LoRa adaptations. They send their LoRa adapters to a local client server. This is a multi-server situation, right? The local clients kind of do a secure aggregation of these LoRa adapters. They have a federated LoRa, but that's only for a part of the chunk of the model, not for the entire model. The entire model is kind of this part and this part glued together. That's when you have the entire large language model. So you're doing local aggregation on the client side that is sent to the server. With the server, you do split learning, which means you forward prop, and then the server learns further, you back prop, and you back prop again. Okay, so that's split LoRa. And this brings up this plot. And then we were looking at how it was performing in comparison to federated LoRa. And I was kind of expecting that we would have similar performance, give and take, up to like the empirical thing. But it was consistently showing, for some reason, split LoRa was doing much. So this is a metric is called perplexity. Smaller is the better. So split LoRa was somehow showing consistently better improvements over federated LoRa. And something seemed not very intuitive to me based on how split learning and federated learning in general were performing. But in the LoRa setting, we were seeing this gap. And that was the reason we were wondering if there was something in the way the federated LoRa is being done currently that might explain this gap. And one of the factors that explains this gap is this inexact averaging, for example. Right? So there are a few things that you do differently with LoRa, and then you'll see more of like a similar performance between split learning and federated learning that we would expect. while there's always these other efficiency kind of trade-offs that you'd have between SL and FL. Okay, so a quick segue into, what time is it, by the way? Okay, so I'll kind of, yeah. Okay, so quick segue while I conclude on this one is what is happening in the MLAS, like machine learning as a service kind of a pipeline, right? So this is kind of like your devices, smart devices, we talk into them. This problem is about privacy during inference, not during training, okay? So this privacy during inference. So far, all you heard about is this important problem about privacy during training, right? Privacy with respect to training data is different with respect to inference data. So in the training setting, in the inference setting, you already have model weights, and then you send some data in that's encoded, and that data is sent to the server where the whole process happens, and then you get the answer back, right? So you need to get privacy with respect to this inference data. Okay, so how do we do that? That's our second work. Currently, so this is our NeurIPS work from 23. There's currently, most work right now is with respect to DP and like privatization on the weights as opposed to the embeddings themselves. What about for activations? There's a bunch of pipelines which are currently developed, which are like heuristics about privacy, but not final privacy guarantees themselves. So the way we do this is called post hoc privacy. We take in existing models that do not give formal guarantees of privacy, and then we plug in some computation that gives you formal guarantees of privacy. So you don't have to retrain from scratch. You can use models that are currently existing. Okay, so this is based on differential privacy, which you heard about, which is the fact that you want to control that the output PDFs are very similar if your inputs are similar. Okay. So the key is as follows. To conclude, there is a proposed test release method that was developed in 2009. It was kind of a seminal paper where if you did not know how much noise to add in order to get DP, you can kind of propose an amount that you'd like to add, but then there's a framework that gates in whether that noise is enough or not. There's the test part. And then you release accordingly with that amount of noise. If what you're proposing is not enough, then you have to change it accordingly. But this doesn't fit well with large neural networks because it's very hard to even figure out what to propose. That's our improvement that we did in our NeurIPS paper, which is the extended proposed test release. With the technical details put aside, it allows you to propose a better sensitivity bound so that you can test and release inference queries. Okay, so I will conclude with that, but the other thing you should be checking is our upcoming work on data markets from this year's NeurIPS, which is a way to trade data. LLMs are hungry about data, and this work is more about how do you trade data. Check out our work, and I'll conclude with this. Thank you.